Hi, this is the continuation of week 11 lecture, and where we finish off if we mention that why material that is strain hardening sensitive, you have to have a deeper depth of cut. Okay, as you can see, the high B and N after the workpiece has been machined or processed, with high B and N the hardness is higher, and then with low B and N the hardness is lower on the newly generated surface. So to continue, we are going to look at the effect of strain hardening sensitivity on cutter path during milling. So this is a milling operation where you have a tool. So this is the tool rotating, okay, between 2000 and 6000 RPM, and the workpiece material is in linear motion in X or in Z direction. Or if you go to YouTube, you just type the word milling, you will see the process. So in milling, the tool is rotating and the workpiece is under linear motion. Okay, the tool is rotating, different from turning, and the material is under linear motion. And there are two types of milling configuration: down milling and up milling. Okay, one is known as down, the other one is up. So if you look at the B and N value, if you have low B and N, it does not matter whether you do up or down milling or up and down milling, which I'll explain to you later. If you have high B and N, you only can use what? Down milling. Okay, what do I mean by down milling? So this is schematics of down milling. In down milling, the undeformed chip thickness start from thick and go to what? Thin. Okay, this is the tool motion. This is the tool motion. And if you look over here, I have superimposed the hardness value, okay, the hardness distribution. Okay, so this is the hardness distribution. And when the material is strain hardened sensitive, right, you have to do down milling, or we call it climb milling. It's because if you do down milling, the workpiece will hit the tool, will hit the workpiece where it's softer. Okay, as you progress further, the hardness increases, but it's okay. Why? Because the temperature in theta 2 is higher than theta 1, so it's okay. So coming back to down milling again, the undeformed chip thickness start from thick and go down to thin. And this is the actual milling configuration. Okay, so this is the path of the cutting edge. Okay, the cutting edge location, 1 revolution, 2 revolution, 3 revolution, 4 revolution. That's why you see the undeformed chip thickness is going from thick, T1 is thick, and T4 is what? Thin. So further on, this is the motion of the workpiece, and this region is the tool and workpiece engagement region. So the tool and workpiece engagement region, okay, the workpiece feed direction is the same as the tool. So if you look over here, the tool is rotating in this direction. The feed direction is also the same during engagement. And the chips are deposited over here. Okay. So when that's the case, the chips are hard than the workpiece. So you have to be careful. So these are very hard, but it's deposited behind. It's okay. In up milling, the tools start from thin to what? Thick. Alright? The undeformed chip thickness start from thin to thick. So when that's the case, you can see the problem. It's going to hit it when it's what? When it's very hard. And as usual, Q2 will be greater than Q1. So doing up milling, okay, you see the undeformed chip thickness start from thin and it go up to what? Thick. Okay, and you can see if this is the vector of the rotation of the tool, this is the motion of the tool, and during the engagement, the feed direction is opposite to the tool rotation, and the chip will fall in front. And when the chip fall in front, is bad news because the chip can be carried by the cutting edge and hit on the workpiece again. So coming back to where we were regarding strain hardened, because now you know the difference between climb or up and down milling. So material with high strain hardening sensitive, down milling must be used. This is due to lower stresses acting on the tool, right? Down milling, if you go back to down milling, it's hitting on the hardness which is softer, okay, or lower. Then in order to cut down on up milling, we have to adjust the cutter path. So what do I mean by cutter path? So this is our workpiece material. and this is our tool. So the red line is our cutter path. So when the tool move from here to here, it goes me, and the tool is rotating in this direction, right? So it goes from right to left, it goes me, okay? Then what you see down here, if it goes from right to left with the tool rotation, it's doing up milling, and then when you do the next pass, it is down milling. Now this only can be used in low BNN. In high BNN, what you have to do is you have to start from here. Okay, I'm going to draw. And then when you cut here, this is down milling, down milling, down milling, down milling, down milling, down milling. Then it has to go up again, go over the other side, come down again, and then down milling, down milling. So this is what we call by modding the cutter path. Again, come back, add time, then we start cutting again, and then the next pass, so on and so forth. Okay. Now, how about slotting? So slotting is creating a channel like this. Whenever we do slotting, it's always really difficult. Why is that? Because if the tool, so you have a tool over here in slotting, right? The tool have to pass through. Down here, right? You see the undeformed chip thinness go from thin to thick, and then over the other side it goes from thick to thin. So it's a mixture of up and down milling. So the only way to do this is to do trochoidal cutter path. So trochoidal cutter path, in a sense that your tool will move this way. Okay, your tool path will move this way. So this is the only way to machine strain hardened sensitive material. Okay, by using this cutter path. So when it's strain hardened sensitive, you have to do trochoidal, okay, cutter path. You can YouTube trochoidal, you can see better what I mean. And lastly, we're looking at strain rate sensitive. Okay, so what I've done down here is we have materials. Okay, so we look at aluminum, hardened hot work steel, and nickel-based superalloys. The C value decreases when you go higher. Okay, when you go aluminum, the C is the lowest, nickel is the highest, and i.e. it is more strain rate insensitive when it's aluminum. So you can see in terms of strain rate sensitivity, it will affect your what? It will affect your range. For nickel, you only can do 30 to 60 meters per minute because it's very strain rate sensitive. For hot work die steel, the range widen to 150 to 300. For aluminum, it can go from 600 to 7,500 because it's strain rate insensitive. Right? It's strain rate insensitive. So strain rate sensitivity affects the range of cutting speed. High strain rate sensitivity will tend to have a more narrow cutting speed operation bandwidth or range. And in terms of thermal softening, it depends on your N value. Okay, if the thermal softening index can be used to determine if increasing speed will benefit to reduce the stresses of the tool. So if M is smaller than 1, increasing, okay, so if M is smaller than 1, if M is smaller than 1, when you increase the cutting speed, it might help to soften the workpiece. If M is greater than 1, increasing the speed will not help you at all. Okay, and that's all for 303. Thank you so much.